Hello, this is Jack Jackson. In this video, we're going to be talking about comparing Euclidean, hyperbolic, spherical, and taxicab geometry, specifically the things that we've been talking about in the earlier playlist so far. So these are four basic geometries that we're going to be studying quite a bit in the rest of these playlists in this geometry section and in my college geometry course. Of course, the Euclidean geometries are familiar geometry that most of us know about, and it's been around for many uh, centuries. Hyperbolic geometry, we're going to be using the Beltrami-Poincaré half-plane model that we have introduced in earlier videos. We've also introduced some GeoGebra and Leonard sphere models for spherical geometry, and traditional taxicab geometry is what we're going to be looking at as well. Um, there is at least one other slight variation on taxicab geometry that I have seen, and I have seen multiple representations of hyperbolic geometry, but these are the versions that we're going to be using in my presentation of this material. So we're going to talk about some things that we've talked about so far, the incidence postulates a little bit, how they relate, and the concepts of distance, basic things like points, lines, and planes, and so forth. And so these are the parts that we've talked about so far. We'll compare some of these things a little bit more in detail as we learn other topics in all four of these geometries simultaneously. So some things that they have in common, there are infinitely many points, lines, and planes in all four geometries. Any three non-collinear points determine a plane, and in a particular plane, there exists a unique perpendicular line to any given line through any specified point on the given line. So these are some things that are common to all four geometries. What are lines? Well, Euclidean lines are Euclidean lines. You probably know what they look like. They have equations of the form ax plus by equals c for some real numbers a, b, and c. And any two distinct points determine a unique line. In hyperbolic geometry, there are two types of lines. Lines are Euclidean semicircles with centers on the half-plane edge, and of course open endpoints on both that are also on the edge. And or the other kind is that they're open ascending rays perpendicular to and starting on the edge, with of course the point on the edge not being part of it. And any two distinct points again determine a unique line. In taxicab geometry, lines are Euclidean lines, and any two distinct points determine a unique line. In spherical geometry, lines are Euclidean great circles. In other words, the intersection of the sphere with the Euclidean plane, which contains the center of the sphere. Or in other words, a circle of radius 1, because we're taking our unit sphere as our plane, centered at the origin of the sphere as at the center of the sphere as a Euclidean object. They are also circles of radius pi over 2 in the spherical plane. And there we have to modify our postulate a little bit. And so we have to say any two distinct non-antipodal points determine a unique line. So a pair of antipodal points are contained on infinitely many lines. So what about a line segment? A line segment is defined to be a set of points consisting of the endpoints A and B and all the points between A and B, where A and B are distinct non-antipodal points. That's going to be our actual definition. And in the case of hyperbolic, Euclidean, and spherical geometry, a line segment is the unique shortest continuous path between any two non-antipodal points. And it is the line segment with those 2 points as endpoints. In taxicab geometry, it's one of the shortest paths. It's a shortest path between 2 points is the Euclidean line segment between the 2 points, but it's not the unique shortest path. Infinitely many points of the same length can be created. Infinitely paths of the same length can be created using some of them using only horizontal and vertical line segments, but using all kinds of different paths, we can make paths of equal length as measured by the taxicab metric. In Euclidean geometry, line segments are continuous portions of a line, and they can be anything in the length interval from 0 to infinity. Finite length, but any positive finite length. Any two distinct points determine a unique line segment with these points as endpoints. That's also true for hyperbolic geometry. Line segments are continuous portions of a line, and they have lengths anywhere from anything in the interval 0 to infinity. Any positive length can be obtained. And any two distinct points determine a unique line segment with these points as endpoints. Remember, when we say determine a line, we mean they're given 2 points. There exists exactly one line containing those 2 points. That's going to be also true in taxicab geometry. Line segments are continuous portions of a line which have lengths in the interval 0 to infinity. Any two distinct points determine a unique line segment with these points as endpoints. In spherical geometry, line segments are continuous portions of a line, but they can only take on lengths between 0 and pi, non-inclusive. Okay, in less than pi and greater than 0 for our lengths of all line segments. Any two distinct non-antipodal points determine a unique line segment with these points as the endpoints. If you take two antipodal points, there is no line segment with them as the endpoints. All right, how about distance? Well, distance is non-negative and unbounded in taxicab, hyperbolic, and Euclidean geometry. We have bounded metric, and the Euclidean metric of course, is basically the Pythagorean theorem for distance, or Euclidean distance formula. It's delta x squared plus delta y squared, and then square root to get the distance there. Whereas in taxicab, distance is the absolute value of delta x plus the absolute value of delta y. A little more complicated to find the distance in hyperbolic geometry, but it's still non-negative and unbounded. It used the cross ratio to measure the distance. If you take AB, you take the natural log of the Euclidean distance from A to M times Euclidean distance B to N divided by the distance A to N and B to M. These are Euclidean distances. And if they've got different first coordinates, if they got the same first coordinates, it's just the natural log of A, the distance from A to M and B to M. In other words, it's the natural log of the y coordinate of A divided by the y coordinate B, where M and N are intersections of the half-plane edge in Euclidean circle, or as Euclidean objects, or Euclidean line containing the hyperbolic line through the 2 points, and the distances of the formula are Euclidean distances again. So you'll see an earlier video for more explanation about that. In spherical, the distance is non-negative, but it's bounded to at most pi. The farthest 2 points can get apart is pi, which is half the distance around the sphere. And that's using a sphere radius 1. If we use a sphere radius 1, which is what we're going to do, then the distance is the Euclidean arc length, which is also the same as the angle measure of a central angle intercepting the arc measured in radians as a Euclidean thing. So as a Euclidean thing, take the point, go to the center of the sphere, and then to the other point, measure that angle in radians, and that's the same as the Euclidean arc length, since the radius of the sphere is 1. And so that's going to be the distance there, which is also the Euclidean arc length. Rays, array AB, the arrow over it, is defined to be the union of the line segment AB and the set of points C such that B is between A and C. That's the formal definition in all 4 geometries. A is the endpoint of array. Array is going to be then basically a half line, and A and B are distinct non-antipodal points. So in Euclidean geometry, ray is just half a line, has infinite length, continuing forever in one direction but not the other. And taxicab geometry, a ray is also a Euclidean ray, so they're the same thing. We would use the same tools for those in GeoGebra. Now, in Euclidean geometry, we have that, but in hyperbolic geometry, a ray is a half line indicating an infinite length. It won't be an infinite length as a Euclidean length, but it'll be an infinite length measured in hyperbolic measurements. It can be a Euclidean arc from a circle centered on the edge with the endpoint in the plane and extending to but not including the point on the edge. And it can be a vertical ray, Euclidean array, with the endpoint in the half plane pointing up. It can also be a vertical Euclidean line segment with an endpoint in the plane, an open endpoint on the edge. So sort of three different versions there. And that's hyperbolic in our model of hyperbolic geometry. Spherical geometry array is half a line. It's a Euclidean semicircle with included endpoint and included endpoint at the antipodal point of the endpoint. It has a length of pi. What about intersecting lines? Well, in Euclidean geometry, two distinct lines in a plane may be parallel, meaning they do not intersect, and they're in the same plane, or they could intersect in exactly one point. That's, of course, since Euclidean lines, taxicab lines are Euclidean lines, you get exactly the same result there. And that's also true in hyperbolic geometry. Two distinct lines may be parallel or intersect in exactly one point. But in spherical geometry, any two distinct lines that are in the same plane always intersect in exactly 2 points, and those will be an antipodal pair. They'll be a distance of pi apart, like the North Pole and the South Pole. So there's a quick side-by-side comparison of those 4 geometries, at least some of the things that we've studied thus far. Hello, in this video we're going to be talking about a formal approach to distance and order. So we're continuing back, now going back to our formal development of unified geometry. And so we've kind of developed some models for 4 different geometries, that is Euclidean, hyperbolic, spherical, and taxicab geometry, and they're all 4 going to work with what we've got coming up here formally. So we're going to add some existence, we have some existing postulates for existence and incidence, and we're going to add to that some things about distance and order at this time. We're going to start by defining a distance metric. So a distance metric is a function, d, mapping a set of ordered pairs of points in a geometry into the set of real numbers such that for any 2 not necessarily distinct points a and b in the geometry, the distance from a to a is 0. In other words, the distance from a point to itself is 0. And the distance from a to b is positive if a is not equal to b. So we would say it's positive definite. Distances are non-negative. And the distance from a to b is the same as the distance from b to a. It has a symmetric property. In other words, the distance from a to point b is the same as the distance from b back to point a. And the output of this function is called the distance between the 2 points, and we'll use the notation ab for the distance from a to b. So if you write AB with no symbol over the top, you're talking about a number, a real number, a positive real number, or 0 if A and B are the same. Okay, so it's a number. So notice that a distance metric is a function and a distance is a non-negative real number. Neither is a geometric figure. In our notation, AB is a distance, it's a non-negative real number, while the line, AB with a line over it, the line segment, which we'll define in a bit, like this, and the ray AB are geometric figures. And we'll see below how we define those in some cases. Line will be an undefined term, but we'll define a line segment and a ray. And be sure you use the appropriate equation editor in Microsoft Word. Use the accents under there to get the appropriate symbols on top. Okay. You can actually just copy and paste these things here as well. Okay. So you have 2 capital letters representing points, and we have the appropriate symbol on top if we're talking about a line segment, or array, or no symbol on top if we're talking about the real number, positive real number, it's a distance. Be sure you use proper notation. That's an easy thing to get correct, so please do that. We say that the distance metric d is unbounded if and only if the range of d has no upper bound. In other words, if d is onto the interval 0 to infinity, as it is in Euclidean, hyperbolic, and taxicab geometries. We say that the distance metric d is bounded if and only if the range of d has an upper bound. In other words, if d is onto like 0 to pi as it is in spherical geometry. If the geometry has an unbounded metric with an upper bound of u, then the 2 points a and a prime with a prime equal u are said to be a pair of antipodal points or polar opposite points. We will denote the polar opposite points by A and A prime, and typical points are points on a single spherical plane which are as far apart as possible. Examples of typical points are on Earth are the North Pole and the South Pole. Um, Notice that typical points do not exist if the metric is unbounded, as it is in Euclidean taxicab and hyperbolic geometries. So it turns out the Euclidean hyperbolic and taxicab geometries have an unbounded metric, and spherical geometry has a bounded metric. In our treatment of spherical geometry, we choose to let the upper bound u be pi. This choice for an upper bound of pi for the distance metric is consistent with the model embedding spherical geometry in a three-dimensional Euclidean space, so the spherical plane is a unit Euclidean sphere, radius 1 unit. Then the distance metric is measuring distances consistent with measuring Euclidean arc length. Also consistent with measuring the angle as a central angle and Euclidean angle measured in radians. Another property that we'll prove later is called the triangle inequality. For any three not necessarily distinct points A, B, and C, the distance from A to B plus the distance from B to C has to be greater than or equal to the distance from A to C. A set of points with the distance metric satisfying the triangle inequality is called a metric space. Metric spaces form an area of mathematics that is a source of study. One thing generated by metric spaces is a concept of an open set, for example, open intervals on a real number line. If we generalize the concept of metric spaces to focus on the properties of open sets, then we generalize to a topology, which is a major area of study in mathematics. Metric spaces and topology are thus generalizations and abstractions of some of the basic geometry concepts that we're studying here. We will later prove that our unified geometry satisfies the triangle inequality. Save that for later. If a geometry has a distance metric, then we can use it to formally define what we mean by between. But recall that in a strictly synthetic approach, for example, in Hilbert's approach, between is left undefined. So our definition, now that we have a metric for our geometry, a distance metric, we say that point B is between points A and C if and only if A, B, and C are distinct collinear points, and the distance from A to B plus the distance from B to C is equal to the distance from A to C. We notate this as A dash B dash C. So when we read that, B is between A and C. Furthermore, we say that A dash B dash C dash D if and only if each of the following between this relationships hold. B is between A and C, B is between A and D, C is between A and D, and C is between B and D. Notice that this definition has three parts. The points A, B, and C must be distinct, they must be collinear, and the relationship among the distance holds. That is, AB, the distance from A to B plus the distance from B to C has to equal the distance from A to C for B to between A and C. We will see below that all three of these conditions are needed. So here's a basic Euclidean geometry with D-E-F-G. So notice F is between E and G, and it's also between E and H. G is between F and H, as well as between E and H. So there's an order to them. And you can see that all these definitions work out. For example, the distance from E to F is 2, and from F to G is 3, and so those two add up to the distance between E and G. They're also distinct and they're collinear. And you can check out all the other ones add up appropriately. Now here's a finite geometry example. Consider the following finite geometry with a distance metric where all the 4 points are on one and only one line. So we have the points A, B, C, and D. The line is the set A, B, C, and D. And let's say we have distances. We can define that. AB is 2, the distance from A to C is 5, the distance from A to D is 6, from B to C is 3, the distance from B to D is 4, and the distance from C to D is 6. So since this geometry has a distance metric, by definition, the distance from a point to itself is 0. And so xy equals yx for any of the points x and y in the geometry. This gives us a mapping from any ordered pair of points to a subset of the non-negative real numbers as illustrated in this table. So distance from A to A is 0, distance from A to B is 2, distance from B to A is also 2, and so forth. Any such table like this will have zeros along the diagonal and will be a mirror image across that diagonal. Remember that all points are collinear, so that portion of the definition of between is satisfied, and we can illustrate distance by numbers on edges here. So all these are just indicating distances. All these points are on the same line. What betweenness relationships exist? Well, let's see if you can figure these out on your own before you come back and look at it. Press pause now. Okay, hopefully you've looked at this and see what we got. Well, let's see. Notice that from A to B is 2, and from B to C is 3, and from A to C is 5. So B is between A and C. These two distances add up to that. But if you take really, that's the only betweenness relationship we have. No, we have one here. B is also between A and D, because this is 2 from A to B, and from B to D is 4, and from A to D is 6. But now among these 3 points, B, C, and D, there's no one is between the other two. The distances are 4, 3, and 6. For B to C is 3, B to D is 4, C to D is 6. No two of those add up to the third one, so there is no betweenness relationship there. So, depending on the geometry, there may not be a betweenness relationship, even when we do have a distance metric. Why do we have the part about collinearity? Well, it turns out in Euclidean geometry, if the distance from A to B plus the distance from B to C is the distance from A to C, then the points A, B, and C must be collinear, and B is between A and C. So you might think, well, why do we even need the collinearity part of the definition? Well, the following example in taxicab geometry shows that we need the collinearity part, because in taxicab geometry, there are examples of points A, B, and C with AB plus BC equals AC, but the set ABC is a non-collinear set. So here's an example here, I, N, and L. The distance from I to N in taxicab geometry is 8. 1, 2, 3, 4, 5, 6, 7 to the right and 1 up is 8. This one is 5 right and 5 up for 10 from N to L. And the distance from I to L is also 18, right? It is 6 up and 13, let's see, 7, 8, 9, 10, 11, 12 to the right. Okay, so for a total of 18. But we don't want to say N is between these because it's not on the same line. We want between to mean the same thing it does in Euclidean geometry. So J and K are between I and L, but N is not. Okay, otherwise we have a really funky line segment situation. Okay, so we want line segments here to be the same as they are in Euclidean geometry. Okay, so we need the collinearity part of the definition. Now things get a little stranger in spherical geometry. So in spherical geometry, every line is just a Euclidean circle of radius 1. So if I want to take a line, I can model it by just looking at the unit circle here at a plane. And distance is measured as Euclidean arc length of the smallest arc of the circle with these two as endpoints. Since the radius of the circle is 1, this is the same as the Euclidean measure of the Euclidean central angle that intersects these 2 points measured in radians. So here's an example where P is between O and Q. Okay. So in general, the basic betweenness properties exhibited by Euclidean geometry are shared by any geometry satisfying the postulates thus far if the geometry also has an unbounded metric. So for example, betweenness properties are essentially the same in Euclidean, taxicab, and hyperbolic geometries. For example, when the metric is unbounded, given any three distinct linear points, exactly one of the three is between the other two. However, if the metric is bounded, as in spherical geometry, some of the betweenness properties are a bit different. For example, it's possible to have 3 points with no betweenness relationship, as we see in the following example. So these 3 points here, there's no betweenness relationship. The distance from here to here is about 2.4. That's from O to P. From P to Q, it's about 1.7. And from Q to O, it's about 4.1. Well, no two of these add up to the same as the other one, even though they are collinear. And of course, the reason is the distance is measured as sort of the shortest distance to get there, right? We do that. So if we did a line segment from O to P, it would not include Q. Okay, so it is possible to have no betweenness relationship at all. And that happens certainly in spherical geometry. So to be sure that we still include spherical geometry in our study of unified geometry, we have to be a bit more careful with the statement of some of the propositions and definitions related to distance and betweenness. Including spherical geometry in our study of unified geometry will also require us to go back and actually modify one of the earlier postulates and one of our earlier propositions from previous notes. Okay? And we'll discuss how these concepts manifest themselves in spherical geometry as we get going a little bit further on down here. Okay. So important note on studying definitions. Note that the statements of definitions, postulates, and propositions in any branch of mathematics must be made very precisely. Often even changing one word will result in a statement that has a different meaning. When studying mathematics, you should always pay special attention to memorizing the definitions. And geometry has well more than its fair share of defined terms. One thing you should do every time you can encounter a defined term in our study of geometry is to make yourself a flashcard with the name of the term on one side and the definition on the other side. You should also make a flashcard or flashcards with the name of the term on one side and a representative illustration of it on the other side, perhaps one for each of the geometries we're studying. Use these flashcards to help you memorize the definitions. Carefully stating definitions will likely be a part of quizzes and exams, and do not neglect this memorization. In the past, students have had a surprisingly difficult time stating definitions precisely. For example, can you precisely state the definition of a circle right now from memory without looking it up back earlier in these notes? Do you think you could do that before our next class? Now that we have a definition of between, we can go on to talk about what it makes to be a line segment.